This is Computer Programming 1 from the University of Washington. I'm Martin Dickey. Our topic today is multidimensional arrays. There's something a little different about this topic compared to what we've been doing so far. Just about everything we've studied up to this point have been things you use every time you sit down to program. Expressions, control flow statements, variables, functions. Even arrays are used very commonly. But multidimensional arrays won't be used in every program. When you need them, however, it's very good to know how to use them. Today we'll start by reviewing 1D arrays and then discuss how 2D arrays are declared and used. We'll spend some time talking about 2D arrays as parameters and then conclude with a technical discussion of how 2D arrays are arranged in memory. Along the way, we'll look at a couple of examples that I hope you'll find interesting. Let's review. An array is an ordered collection of values, all of which have to be of identical type. We name the collection and we number the elements. This turns out to be an extremely convenient thing to do. We don't have to think up individual names for all the variables in our program. Arrays are a natural choice for organizing large numbers of values. Sometimes, however, we have an additional structure in the data that we'd like to be able to take advantage of when we program. One such structure is a table or a matrix of data. That is some kind of two-dimensional arrangement with rows and columns. A spreadsheet is a good example of this. Tables occur very often in everyday life in things like calendars as well. In C, we can express data organizations like this using a two-dimensional array. It's also possible to program higher dimensional arrays in C, but we won't see any examples in this course. Let's define two-dimensional arrays: an ordered collection of values of identical type. Name the collection, number the elements. Maybe you're going to object that this sounds just like our definition of arrays, and it does. It is the same concept. The difference comes in how we do the numbering for the elements. When we have a table like a table of scores for students, we would think of one direction of the table as representing students and the other direction representing the homeworks. So this might be the way we would picture it. Each student is one row of the table. Each homework is a column. If I want to know what score student 1 got on homework 2, I would look at the intersection and find a value of 25. So when we do the numbering, we're going to have to specify two numbers, both the row and the column. You might guess that this will be similar to what we did with 1D arrays, and you'd be right. All we have to do is show two integer expressions, each with its own curly brace. We think of the first one as being for the column, and the second one as being for the second one is for the column, the first one is for the row. That's important enough that I should repeat it with an example. Let's look at score sub 6 sub 3, the second example. This means go to row 6, the bottom row in our case, column 3, the last column, and we see that the value there is a 12. These two-dimensional array references can be used as expressions as we did with one-dimensional array expressions. So in the last example, I find the value of score sub 3 sub 0, row 3, column 0 has a 15, and then I can use that within a larger expression. In some programming languages, you don't need two sets of brackets. I could say something like 3 comma 0. If you do this in C, it will sometimes compile and sometimes not, but it will never give the right answer. So please don't forget to have two sets of square brackets. We've seen how to reference a 2D array. Let's talk about declaring one. It's very much like declaring a 1D array, except that we need to tell the size of the second dimension. So here I've declared an array. Its name is score. The type of the elements in the array is int. And the dimensions are max students rows and max homeworks columns. Of course, these aren't reserved words of C. These are constants that I would have to have defined earlier in the program. Now, once I've done this, I could write a program to use the array. We'll see examples of that shortly. Let's take up a little terminology first. At the top of the screen in the yellow box, you see the general syntax of the array declaration. It's typical of what we have come to expect from C. We start with the type, we follow that with a name, and then we conclude with any qualifiers. In this case, the two dimensions, the rows and columns. To keep the slide a little shorter, let me redeclare score using constants, if you'll allow me, instead of the pound define symbols. So if someone asked you, what is the type of score, the correct way to answer that would be, score is a two-dimensional array of ints of size 80 by 6. All of that information is needed to use the array. The elements of the array are the individual values inside, and to get at them we'll always have two subscripts. There is an alternate way we could view a 2D array that's sometimes useful and sometimes not. We could think of the overall array as an array of its rows. In that case, we would say that score is an array of size 80. It contains information about 80 students. Then each row itself is also an array of integers. In our case, an array of size 6. Most problems, however, don't require this structure, and you're usually best off just thinking of an array as a two-dimensional object. As with 1D arrays, we have to declare the array to be as big as we ever expect to need it. And this means that frequently we won't be using the entire array. We may not be using all of the space inside of it. The declaration tells the maximum capacity of the array. But the current size is something that you as a programmer will have to keep track of as the program progresses. Otherwise, you would run the risk of accessing something outside the array bounds. Just as C does not check array bounds for 1D arrays, it doesn't check them for 2D arrays either. And you have the same programming task of making sure you don't step outside the array. Let's go back to our example of students and scores, and let's write some code that will read in data for student assignments and place it in this array, this 2D array. Now, the idea is that a person, a user, will type in the data needed. The program will get that data with the scanf and put it in the right place. In order to make this work, the program has to know what order the data is going to arrive in. And not only that, but the user on the other end had better know that order too and follow it. When you think about it, there are quite a few ways we could have chosen to enter the data. We might have decided to go across the top from left to right. We could have gone across the first row from right to left equally well. Both would work, but we'd have to make sure that the program and what the user were doing matched each other's expectations. There's also no reason why we couldn't have started with the bottom row and had the user type that in first. Let's do it this way. Let's have the first thing that the user types be the number of students so that we know what to expect. Then, the number of assignments. Finally, we'll have the data for each student. And although I didn't specify it here, the data will come in a left to right order. Because we're going to process something repetitively, within each student, your instinct might be that a nested loop is the right kind of control structure. And that's correct. With 1D arrays, we saw that a single loop, a simple loop, was a very frequent control structure. And in the same way, a nested loop will often be exactly the right structure for a 2D array. Let's refresh our memory on what the array declaration looked like, and then let's declare some variables that will be useful later on. Of course, when I first developed this program, I might have written the code and then discovered the declarations as I went along. But in the presentation now, I'll put the declarations on this slide. You might want to have a hard copy of this near you as we go through the example. Okay, so we specified that the user's first piece of data will be the number of students and the number of homeworks. So a scanf can catch both of those at once. This won't be inside a loop. This is one-time information. After we've done this, we can now start thinking about constructing the loop. Each time through it, we'll get one score. We'll need to keep track of which student that belongs to. Here's the complete code for doing that. We'll come back to the condition at the top in a minute. Let's look at the if statement, body of the if statement, which contains the double for loop that's the heart of this algorithm. The first for loop iterates over students, starting from student 0 and continuing until it reaches n students. Now that's a value that was just typed in by the user. There were n of those n students. If we're counting from 0, then the right range is 0 to n students minus 1. That's why we have a less than rather than a less than or equal to. In the second loop, we'll be going across the columns. Each time through that loop, we'll read in exactly one item of data. Now, we could read this into a temporary variable and then store it in the array, but we don't have to. We can put it in the array directly. Of course, we have to know where to put it. We have to know two things: the student index and the homework index. Those are exactly the same as the counting variables we're using for the for loops. So at any given point in time, we look at the expression score sub I sub j. That will refer to row I, the student number, and column j, a homework number. A little mysterious punctuation appears before the score. This is nothing special. This is the same ampersand we've seen before with scanf and that we now understand with our knowledge of pointers. Scanf needs to know the address where it's going to store the data. The variable score sub I sub j has an address. That's what we have to give to scanf, and that's what the ampersand does. It will pass the address of that variable to scanf. Okay, I think the inner loop now is correct. Let's just go back for a second to the if statement that the inner loop was the body of. Why did I need an additional check, a one-time condition, if n students less than or equal to max students and so forth? This has nothing to do with filling in the array per se. It's a safety check. It's there to make sure we don't step outside the bounds of the array. If the user typed in the wrong number of students by accident or design, we wouldn't want the program to start filling in data outside the bounds of the array. So this action protects us from an error on the part of the user. It would also protect us from a malicious user. Unfortunately, there are such things out there, and loop bounds in C turn out to be one of those vulnerabilities in computer programs that have been exploited by hackers many times in the past. Now, probably n students is less than our maximum students. And probably number of homeworks is less. We don't know for sure. All we know is that they're within bounds as a result of the condition. So part of the array is unused. It might be interesting to ask ourselves which part of the array is unused. We'll be able to answer that precisely if we take the time to go through a trace for this piece of code. In order to do the trace, we have to know what the input is going to be. So let's say that what you see at the top is the exact sequence of numbers that the user is going to type in, one at a time. Here's our table. To reduce clutter, I've drawn it without all the interior lines, but you can imagine that they would be there. So we have rows of students and columns of homeworks. The first number I read in is a 7. Now, a trick question might be, where in this table does that 7 go? That's a trick question because the 7 doesn't go in the table. 7 is the number of students. And the 4 that follows it is the number of homeworks. The 0 is the first value that represents a homework. So if you check this against the code we just looked at, you'll see that when we store that into score sub 0 sub 0, we'll get the 0 stored where it belongs. We'll continue reading in values from the user, the 1, 2, 3, and so forth, until the inner loop condition ends. Now it ends when the inner loop index, j, is not less than the number of scores, which is 4. So the last position I'll fill in on the first line will be column 3. That will end the inner loop. I'll bounce back up, ready to start another iteration of the outer loop, and it begins by incrementing its counter, I, by 1. That puts us on row I. And so the next value read in, which is a 5, will go in the next row. So we'll continue this way. We'll fill in the next row. We'll keep putting values in that row until the inner loop variable j is not less than 4. We'll go up to the outer loop condition, check it. We'll continue, continue, continue. Eventually, we'll find that the outer loop condition fails. Okay? That the outer loop variable is not less than 7, that it equals 7. We're not going to store anything in row 7, even though we have 7 students, because we're counting from 0. So the students go 0 to 6. And now we're done. And now we can sit back and visually answer the question, where is the unused space? As we've constructed and programmed this algorithm, the unused space is to the right and at the bottom. All of the used area is at the top and toward the left. Now, there's nothing magic about this. It's just a property of the way we chose to implement the algorithm. Here's one more example of applying an algorithm to this structure. The problem here is to take the data that we just read in and print it back out. Now, we can't print an entire array. That was true for 1D arrays, and it will be true for all other arrays in C, no matter what their dimension. What we can do, though, is reach in, pick out a particular element with its 2 subscripts, and apply printf to that. To do that, I'll need a nested loop, and if I iterate using the same pattern that I got when I read the data in, I'll be able to print it out in a similar format. To make it look even more like a matrix, I should put a line feed at the end of each row. So that is why the printf \n is not in the inner loop body, it's part of the outer loop body. Passing a single element as a parameter is not difficult. We've seen that already, and it's the same situation as passing a single element from a 1D array. In fact, parameter passing for 2D arrays is almost identical to what we've learned about it for 2D arrays. We can pass entire arrays. The entire 2D array has a name. That name could be used as the argument to a function if that function is expecting a 2D array as its parameters. As with 1D arrays, arrays are already passed by reference, so ampersands are not used in the call and stars are not used in the function itself. One small difference, you might remember that on 1D arrays, the formal parameter didn't have to have a size inside the square bracket. You could leave that out, and you might pass it in as a parameter in a separate variable, a separate parameter. Unfortunately, we can't quite do that with 2D arrays. It's a shortcoming in C that turns out to be quite difficult to get around. There is a case in which one of the two sizes can be omitted, but it's a rather technical case. If you feel you need that, you can consult a reference manual for it. A better rule to remember is when you declare a parameter that's a 2D array, you must always include both sizes. Here's an example of a function that has a 2D array parameter. The problem here is to write a function that reads into an array, let's call it A, grade information for a given number of students and assignments. This might sound exactly like the problem we just solved, and it's very close. A couple of differences are, one, we're asked to do this as a function, so we want to package it as a function and not just a group of statements. The other is that the number of students and assignments is given. The implication there is that we don't read those in as part of this function. They're known to us. That means they must be parameters. So as I look at how the function begins, I see that it would have three parameters: A, the 2D array, n students, and n homeworks. It would be an error of analysis to begin programming this function by scanning values into n students and n homeworks. Here's the code. No surprises whatsoever. This is simply the code from the straight line version we had a little while back. I put it inside the function. This function returns no value, but it doesn't need to. Since arrays are passed by references, when I change the array A with the scanf, I am changing the actual array inside the calling function, whatever its name might happen to be. A will be an alias for that array. When I call the function, all I need to do is give the name of the 2D array. It is not necessary to give subscripts. In fact, it would be incorrect to give a subscripted expression. Look at the call in this example, almost the last line of the program. It says read 2D. The first parameter is score. You go up to the declarations and double check, yes, that is a 2D array. Then you would flash back to the function definition and you would say, yes, the function is expecting a 2D array. That's what score is. That's what its type is. So that's the correct thing to write there. Now, if you wrote score sub and then two integer expressions in square brackets, that would be wrong. It's not just unnecessary, it's wrong. And the why, as with many questions in C, can be answered by looking at the types of things. If I say score sub something, that's no longer an array. That is an integer, a single integer. And I can't pass an integer as the first parameter to read 2D, because that function is expecting an array. So once again, being aware of the types of things can help you answer questions and help avoid problems in your programs. Let's take a different kind of example, a digital image. Now, sometimes when we think of graphics, we're thinking in terms of drawing. We might think of a repertory of geometric figures like lines and squares and circles and so forth. But when the image is finally displayed on a screen, or perhaps printed or sent down the internet, it's not a collection of circles and lines and arrows. It's just a bunch of individual dots. Okay. We call each dot in the image a pixel. And our images are usually square or rectangular, so this is a rectangular grid, which is exactly what we've been talking about today. It's a matrix, a table, or a 2D array. So in processing digital images, a 2D array is the perfect data structure. Let's talk a little more about exactly what the image representation would be. Now, in a color image, each pixel has 3 values. It has a value for red, green, and blue, and it's the combination of those together that give our eye the impression of colors other than those 3. For a black and white image, there's only one value for pixel, and that is either black or white. We can think of that as on or off, true or false. Okay. We will see later in this course how we could package up a 3-dimensional value, like color pixels. Let's stick today with a black and white or a monochrome image, where each pixel is either on or off. And we'll do this by storing the pixel as a 2D array. Here we have an example of an image. It has 12 rows of pixels and 8 across. In order to create a picture, you would have to decide which pixel is on and which pixel is off. This is something that people who design things like type fonts sit down and actually do. Figure out which pixels are on and off in the whole set of type being created. We could also do it to create pictures like the one shown here. Now, once we have this set up, we could do various kinds of processing on it. One thing we might want to do is give it an impression of animation by making the image shift a little bit. So we could make this person look like they were moving by shifting the entire image to the right 1 pixel. Let's give ourselves that as the problem. Okay. Now the strategy will apply. The algorithm will be to shift the columns one at a time. Shift all the pixels in one column, all the pixels in another, and so forth. Okay. Within a particular column, let's go down the rows from top to bottom. Okay. Shift the pixel in row 1, or rather row 0, then the pixel in row 1, and so forth. So that's the overall setup, and that's the overall algorithm that we'll follow. Now, to develop the code, we'll need some definitions. A very common image size, by the way, are the dimensions shown here, 768 by 1024. That's quite a lot of pixels, isn't it? And let's assume that the color white is known to the computer system by this particular value of 255. Okay. Now, developing the code, let's keep our goal in mind. We're going to shift the image right 1 column. Like so many things, now that we know about functions, we should always be thinking in terms of packaging things as functions, so we can call them as needed. Get the code right, get it correct, write it in only one place, and then it can be called from other places. As a function, we would need to pass in the entire image, which is a 2D array. So regardless of what the size is of the image, there will only be one parameter. And notice that following my advice earlier, I've put the sizes in the square brackets in the formal parameter list. Okay, I find that I'll need some additional variables. Now, I'll have to shift all the columns. Let me come back to the question later of what order I should shift the columns in. Let's say that I have picked one column, and now I'm about to shift its contents. We're shifting down the rows, and so I need a single for loop that starts at row 0 and continues to the end. What do I mean by shifting to the right? Well, if you think about the picture graphically, I'm taking that pixel value and I'm copying it into another pixel position that's in the same row, but the column is different. The column is column plus 1. Look at this assignment statement with me and see if that's what happens. So on the right-hand side, it's image sub row column. That's where the data is coming from. On the left-hand side, it's image row column plus 1. So I think that gives the right effect, shifting that 1 pixel, 1 space to the right. That's all we need for a loop. That will take care of shifting. The inner loop takes care of shifting 1 column, and the outer loop will take care of shifting all the columns. Now, when I'm completely finished, nothing has been shifted into the leftmost column because there wasn't anything to shift from. So I'm going to make that column white. Okay, that's just a decision. Perhaps you decide to make it black or some other color instead. To make that column white, I'll have to write another little for loop, iterates over that column's rows, and sets all of them to white. Notice the subscripts on the left side of the expression. The first one is row. That's changing, but the second one, column, stays the same all the time. That's 0. Okay, we left something out of that code. We didn't fill in the exact for conditions on the outer loop. There's a question here. Does it really matter if we shift from left to right or from right to left? Okay. And also, what are the correct loop bounds for this? Are we shifting all the columns from 0 to n columns minus 1, or is it minus 2? Or is it from 1 to n columns minus 1? This is something that takes a little thought. Okay. If you get it wrong, you'll either not shift enough columns, or you may shift where you don't belong. You may access outside the array bounds, or something even worse could happen. Let's think about this picture again. Suppose I shift the columns starting with the leftmost. So picture that in your mind. The leftmost column is all blanks now, and it gets shifted 1 position to the right. So it would be all blanks, but it was blanks before. Now I shift column 1 to the right, and column 2 becomes blank. It's all blanks. Now I shift column 2, which is blanks, and column 3. See what's happening? All we're doing is reproducing the same value in every column. So we're really distorting our image, practically wiping it out. So moving from left to right is not the right way to do it. I need to start on the right-hand side of the picture. Move 7 to 8. Then I can move 6 to 7. Then I can move 5 to 6, 4 to 5. You see why that's safe. And that'll give the effect we want. Okay. With that analysis in mind, we can go back and we can fill in this outer for loop condition. Where do we start? N calls minus 2. Not the last column, but the column before last. And we have call minus minus. This is our post-decrement operator. So we're moving backwards rather than forwards. Okay. Once we have this function, we can start to do other fun things with it. We might want to make the image move off the screen altogether. Just have it walk out of our lives. This is easy to do now. I have a function shift right that can move me 1 column over without distorting or changing the image shape. I'll just apply that as many times as I need to, and eventually the item will walk right off the screen. This is very easy to do. It's just a single for loop. Nothing fancy at all about it. I just have to make sure I do it the right number of times. Notice that the shift right call inside this loop doesn't depend at all on the loop parameters, so it's a very simple thing to set up once you have the loop in mind. As a reminder about technicalities of passing arrays, notice that when I call shift right, I pass it only the variable name, the 2D variable name. There is no ampersand. It's already an array. There are no subscripts indicated. Okay. It's already the type expected by the function shift right. Let's take a little different approach to this subject and think about what's going on in the computer's memory, under the hood. Now, most of the time you don't have to worry about this, but for some people it helps to have a firm mental image of what's happening inside the computer. The computer's memory is essentially a 1D array. The array starts at 0 and it goes to the size of the memory of your computer, which these days is fairly large, maybe 96 megabytes or 128 megabytes, millions of bytes or locations. But essentially it is a 1D array. How can we have a 2D array in our program if memory is actually a 1D array? And the quick answer is that in C, the array rows are stored sequentially. That is, we'll have in memory all of array of the row 0 of the array, all of row 1, all of row 2, and so forth. Let's just show this with an example. Back to our student scores. Let's suppose we have the data already filled in. The way this will look in the memory is something like what I have at the bottom of the screen. I have the first value in the first position of memory, the second value, 15, in the second position. It looks like there's a space there. That really is just the way it shows up on the screen. Followed by 25, 25, and then the unneeded question marks, which are positions not used for this application, but are present in the array. They are memory that is allocated and are part of this array. So the first row is this first set of values. Following that immediately will be the values from the second set, and then the values from the third set, and so forth. Okay. Just a little bonus to give you a clearer picture of what might be happening inside memory. Let's summarize what we have. 2D arrays model matrices or tables of data. The notation in use for 2D arrays is, in virtually all cases, just an extension of 1D arrays. So mastering 1D arrays is important before trying to use 2D arrays. As we've seen with this example, and as I think you'll notice as you solve other problems, when processing 2D arrays, nested loops are often a very natural way to express the algorithm. 2D arrays aren't used in every program, but when you have a problem that needs them, it's nice to know that C will let you do that. Join me next time as we explore more topics in programming.